Hello and welcome to the third lecture of the course Introduction to Data Analytics. My name is Professor Nandan Sudarshanam, and today we're going to be talking about descriptive statistics and more specifically about graphical approaches used in descriptive statistics. Now, before we jump into the content, into descriptive statistics and the different types, it makes sense for us to take a step back and talk more generally about data. What is data, and most critically, what are the different types of data that you will encounter. And it's important to do this because the descriptive statistics that you use and the approaches that you use vary according to the different types of variables or different types of data that you will encounter. And this is a recurring theme in many other aspects of this course. So it makes sense for us to talk about that for a few minutes right now. So data is essentially numbers. Now it can also be texts or symbols, but more often than not you'll encounter numbers which represent some kind of information. And therefore it kind of helps to think of data as values, because values is broad enough to cover numbers, text, symbols. So you can think of data as values of quantitative and qualitative variables. Now the variables themselves can be of different types, and that's what we're going to talk about right now. In statistics, you have various classifications of variables, and so different, depending on who you ask, you'll find different classifications in different textbooks as well. But one broad classification that makes sense and that's very useful for us is to differentiate variables as quantitative and qualitative variables. So quantitative variables are also called as numerical variables, and these variables are essentially the best way to think of them is that they have meaning as a measurement, such as a person's height or weight or IQ, or they can be some kind of a count, such as the number of something, a number of days it has rained, and so on and so forth. But a very intuitive way for me that's always been useful for me is to think of quantitative variables as variables where some form of basic arithmetic, like either adding or averaging or subtracting, kind of makes sense, right? I mean, a definite requirement is that the quantitative variable is numerical, but sometimes you can also have numbers being used as symbols, not as the actual numbers. So as a really simple rule that kind of helps me identify quantitative variables is to say that it has to be a numerical variable, that the values that this variable takes on are numerical, and that some basic forms of arithmetic kind of make sense on such a variable. Now within the quantitative variables you have continuous and discrete variables. Continuous variables are essentially ones where within a certain interval, right, and this is an interval that where the variable could take on values, within this interval any value is possible. If any value within this interval is possible, then this variable is said to be a continuous variable. So let me give you an example. Let's say that the variable we are interested in is the height of students who are registered for this course. And so let's say I go take a sample of 1,000 students and write down and their heights, and so this is a data set that I have. The data set has 1,000 values, and let's say an interval, and the interval you can maybe get that interval from taking the highest value to the lowest value, or you can just as long as it's a real interval that covers this data. The question is any value possible within this interval? And the answer is yes, right? So let's say my interval was 120 centimeters to 140 centimeters. Is it possible that someone who's taken this course could have a height of 135 centimeters? Absolutely. There's nothing about heights that inherently stops people from having that particular height. Now I can go even further, right? I can say, is it possible for someone to have the height of 135.156 centimeters? And the answer is still yes, right? I mean, I might not have a measuring scale that goes to a certain accuracy, but that's a measurement problem. There's nothing about heights that prohibits this value from existing in this data set. So continuous data is essentially one where any value between a certain interval, and the interval is sometimes formally defined as the highest value in the data set to the lowest value. So any value within this interval is potentially possible. Then you have a continuous data set. The second kind is the discrete. So the discrete quantitative data is one where this condition is not true, essentially. And it again helps to think of what kind of a data set would be such that a value, not all possible values are there. And I'll give you another example for that. Right, so let's say that I was interested in looking at the number of people who enter IIT Madras every day. So the number of people who let's make it interesting, the number of unique people who enter IIT Madras every day. So if you come in and go out 10 times, I don't care. You're still one person. So number of unique people who enter IIT Madras on a given day is my variable. And the actual values of this variable I get from doing this kind of a survey or a study for 1 year. So I'll have 365 data points, one data point for each day, which says the number of people who entered IIT Madras. Now clearly this variable is discrete, because let's say there's a lower bound which is maybe 0 people, nobody entered IIT Madras, highly unlikely, but on a given day. So 0 is the lower bound, and the upper bound is some 100,000 or 50,000 or something. Now within this range, can I have, is every value possible? No. You could, for instance, never have a day where 2.5 people entered, or let's say 133.2 people entered, right? So here it's discrete because it's discrete in the sense that only the integer values are possible, right? All the more, you can never have values that are non-integers. So that's an example of a discrete value, and in this particular case it happened to be one of being discrete at the integers, but that's just because of the example I came up with. You can come up with other examples where the variable is numerical, and it's quantitative, but the values it can take up are discrete. We move on to the other class of variables, which are qualitative variables. These are also known as categorical variables, and categorical variables essentially represent some characteristics, some characteristic which can be categorized, which can be grouped. So examples of that are things like a person's gender, right? So that's the variable, and the values that variable can take are male and female. And then you might have something like marital status, or a more interesting one might be hometown of or a state within India. Let's take all the people who've registered for this course from within India, which should be the bulk of them, and the variable we're interested in is which state are you from. So that's the variable, the state that you're from, and the values that this variable can take up are the different states of India. Now the categorical variables, again, because of their definition and their nature, are always discrete, so that should be obvious. But within these categorical discrete variables, there are two classes again. There's the nominal and the ordinal. With nominal, there is essentially, the big difference is that with nominal there is no order. So the great example of that would be this home state, right? Which state are you from? Variable. There is no order which says that Madhya Pradesh is greater than or lesser than another state, and so on and so forth. So these are all the values that this variable can take up cannot be ordered in a sensible way, whereas with ordinal data, by definition of the variable, there is an order. Let me give you an example of that. Let's say that we created a variable for which is a color for terror alert, right? So some countries have this. The terror alert color signifies something, and let's say the possible values that can take is green, yellow, orange, and red. So the variable is terror alert color. Green, yellow, orange, and red are the 4 values that this particular variable can take, where green represents low risk and red represents very high risk. See, so out there, again, it's a categorical variable because it's not like I can do any arithmetic operation on green, yellow, red, this thing. So the variable itself is a qualitative variable. But yet there is some order, right? Because you can say things like, if orange is worse than yellow and yellow is worse than green, that must mean orange is worse than green, right? So you get an idea of, so that's an ordered categorical variable. Whereas with a nominal variable, right, you couldn't say if Madhya Pradesh is greater. First of all, you could never say greater or less than, so creating more complex relationships becomes impossible. So that's just a very quick that's just to give you a very quick idea about the different variable types. So now let's jump into descriptive statistics, right? So descriptive statistics is the idea of quantitatively describing data, and you can do that through various means. You can do that through visualization techniques like graphical representations, tabular representations, but you can also do that through summary statistics. The idea here is that you crunch the data, you work with the data, and come up with 1 or 2 or 3 or 4 different numbers that summarize the data for you. In this class, we're going to be focusing more on the graphical and the tabular representation, and the next module is going to be on the summary statistics. So that's the idea. Now, this is a very good time for us to just quickly review. In our overview classes, we spoke about descriptive versus inferential statistics, and this is a good point to just bring that up again and to kind of have a very quick idea of what descriptive statistics really means. The core idea in this dichotomy is that descriptive statistics focuses or is a way to say something meaningful for the data that you have at hand. So you have some data at hand, whether you call it a sample or population or whatever. If you are making a statement based off of that data, about that data, derived from that data, you're dealing with descriptive statistics. Descriptive statistics do not, however, allow us to make conclusions beyond the data we have. So you can't look at the data, do something with the data, and based off of that make a generalization about potentially the source the data that the data came from. You would need inferential statistics for that. Now, having said this, however, descriptive statistics is still very important because you can't just simply present raw data. It would be very hard to visualize, especially when the data is a lot. When you have a lot of data, you can't just show the data, right? You need to present the data in a more meaningful way, which allows for some kind of simpler interpretation, and that can be through the graph or through numbers. Great. So, and a final point that I just want to make is that descriptive statistics is not just confined to a single variable. It can be about multiple variables. And when you're dealing with multiple variables, a topic of interest is relationships. So how does one variable change with respect to another variable? So in a sense, you'll be doing 2 things, which is summarizing each variable or describing each variable, but you're also interested in showing interrelationship between variables. So So let's go ahead and now that we have an understanding of the different variable types, let's talk about some graphical representation techniques. If one is dealing with a single variable and if let's say it's a categorical variable, a great way of representing data could be through a bar graph. So that's the graph that you see on your left hand side out here. So here, for instance, let's say the example is one where we sent out a survey and asked people what their highest level of education is. And highest level of education would be the variable. The possible values it takes up are high school, bachelor's, master's, and doctorate. And therefore, this is a categorical variable, right? There are only 4 possible qualitative states that this particular variable can take up. And what we're plotting is the number number of responses, or the number of observations we counted in having this value. So you sent this survey out, let's say, to about 50,000 people, maybe 60,000 from the look of it. So, and about 15,000 of them said that their highest level of education was high school. So the height represents the frequency of occurrence of this particular value of this variable. So this kind of a representation can quickly summarize which is more, which is less, and so on. But an interesting thing to note out here is that this categorical variable is actually ordinal, meaning there's an order of going high school, bachelor's, master's, doctorate. Right? You could have flipped the whole graph around, but you would still have that order. There's a sense that a doctorate is more years, I guess, than a master's, and which is more than a bachelor's, which is more than high school, or whatever. So in some sense, the variable itself has an intrinsic ordering. And the good thing is, something like a bar graph allows for that. Just because of the fact that there is this concept of a x-axis, right, makes it very convenient to represent ordinal variables, which are categorical. Another way of representing categorical variables could be something like a pie chart, right? This is an example where, let's say, we looked at the number of students who were in different engineering departments, and your different engineering departments here are mechanical, civil, electrical, and computer science. These are just some random departments I chose. And again, the frequency of occurrence is more represented as a percentage of the whole, right? So this percentage of this full circle is computer science students. And that's the idea behind using a pie chart. And clearly, a pie chart is not very suited for ordinal variables. It's more suited for nominal variables because there's no order. The fact that computer science shares a wall with mechanical and civil is just coincidental. That's not what a pie chart seeks to capture. Sometimes people will keep similar things together, but that's not a requirement. One important thing about pie charts, though, is that usually you want to represent all the values. So if there are some engineering departments that are not being represented, usually a pie chart need not be the best way, because there's an impression that this is all the departments together. So if there are more engineering departments, but you wanted to only show 3 or 4, maybe you could use a bar graph rather than a pie chart. Okay. Now we move on to quantitative variables, and with quantitative variables, you have a couple of different ways of representing a variable. One example is a box plot. So with quantitative variables, remember, it's numerical data, and so you might be interested in representing things like what is the average, what is the variance, and in our class on summary statistics, we're going to go into great detail about it. But for purposes of this, a box plot is essentially something that captures central tendency, which is this red line that's there, and typically that tends to be the median of the data set. and you have the two bounds of the data set, so the top and the bottom of the box itself, and that tends to capture in some way the variability in the data. And the way a box plot does that is by representing the lower quartile and the upper quartile. Now, the lower quartile and upper quartile, in really simple words, is just the 25th percentile and the 75th percentile. So that kind of that range gets captured there, and the whiskers themselves take on different meanings depending on which version of the box plot you're using, but more often than not it tends to be the lowest value and the highest value in the data set, and typically red dots like this represent outliers in the data. The box plot is itself something that will make more sense to you when we talk about summary statistics, because you'll understand what exactly a median means. You'll understand what the different ways of representing spread and outliers and so on. But it helps you at this stage to kind of say that this is one simple way to take a data set which is full of numbers, right? So let's say this data set had 500 or 1,000 numbers, and it looks like these numbers are pretty much within the range of like 25 to 33 or so, and to represent all of these numbers in a single graphical representation. So great. Another way of representing quantitative data is through a histogram. The histogram is what you see on the right hand side, and a histogram is arguably the richest representation of numerical quantitative data, because a histogram essentially says how many data points do you have within this range. So the x-axis out here represents the different possible values that this data set has. So if you take this as 8 through 10, this would be something like 8 to 8.66, and this would be to like 9.33, and this would possibly be 10. So the question is, in your data set, how many data points do you have that have values greater than 8 and values less out here? So another way of showing that, I'm going to try and highlight it, is, so if you're interested in this range right here, this range, so this is 8 and this is 8, let's say 8.66 if I'm reading the graph right. How many data points do you have? Because this is a numerical quantitative data set that have values greater than 8 and less than 8.66, and the answer to that question is, it looks like 6 data points, right? Approximately, maybe 7, maybe, if I'm reading the graph correct. So you answer that question for each of these bins. These are all called bins. Each of these columns are called bins. For each of these columns you answer that question, and what you get is a histogram. And the histogram is the first step towards empirically constructing what we will later learn is a distribution. So once you capture this this entire picture out here, you have a very clear representation of the entire data set. Okay, so again, just keep in mind that we are going to be talking about distributions. We're going to be talking about medians, means, and variances, but keep in mind also that this is the graphical way of representing these things. Great. So now we move on to multiple variables and the last section in graphical representations. And there are three major forms of representing this data, and they are the following. The first is scatter plots. These are very useful when you have two quantitative variables. That is, so two variables which are both numerical. You can very easily represent using a scatter plot, and so in the key thing you should notice in the scatter plot is that it really helps you understand the relationship. It does not do a very good job of understanding each individual variable. So maybe if you'd done a distribution of x and a distribution of y separately, you would have understood those two variables. But what it does a good job is of capturing the relationship between x and y. And in this particular case, the fact that in general when x increases, it looks like y is also increased, or y is also high. Or you can always flip it the other way around. In general, when y is high, x is high. When y is low, x is low. So that relationship gets captured, and for that reason, this is a great graphical representation of two variables. Usually, you can extend box plots. If you feel like one of your variables is categorical and the other is quantitative, and so you're not just you're interested in, let's say, one variable which is country and another variable which is some indicator, let's say, of the economy or crime or whatever. I've just called it values here because it doesn't matter, but this variable is continuous. Right? I should say it's quantitative. I don't know if it's continuous. It could be continuous or discrete. But this variable is quantitative, whereas this variable is qualitative. So one great way of comparing different qualitative variables which have data sets that are on a quantitative scale is to perhaps use multiple box plots on the same graph. And that gives you not just an idea of how on average these countries are different, but are they also different in terms of their variability and their outliers and so on and so forth. Finally, we come to the use of contingency tables out here on the extreme right, and the idea here is that when you have two categorical variables, and what you're interested in representing is the frequency of occurrence. So the frequency of occurrence is the theme of the data set. Then contingency tables are great ways to do that. So an example that I have come up with out here is how many people, let's say you go to a company and you take a survey of all the managers working in the company. You might be interested in asking how many of them have MBAs. So Y represents yes, they have an MBA, and represents no. Clearly, this is a categorical variable, right? It has only two states. Similarly, you could say before these people joined the company, did they have work experience? Before they joined as managers, and the answer could again be yes or no. So that's also a categorical variable. So here is an example where you have two categorical variables, and what you're interested in is how many people belong to each combination. So how many people have MBAs and had work experience before joining? How many people had MBAs, did not have work experience before joining? And so this can be a complex data set, but it's very neatly summarized in a contingency table. And that's something that could be quite useful. So I think that's about it for graphical approaches to representing data in the module Descriptive Statistics, and in the next class we'll be looking more at summary statistics as a means as a submodule in Descriptive Statistics. And then we will then move on to inferential statistics. Great. Thank you for joining me, and look forward to seeing you in the next lecture.